a student at UCLA. We didn't have time to eat, or some people were so busy they didn't take time to eat. So somebody got a Reuben out of the vending machine. And, you know, in UCLA they have, or they used to anyhow, have microwave ovens, you know, there too. And he said, I don't have time to microwave it. He ate a raw Reuben. I mean, an unheated Reuben. I don't know. To me, that's, you know, maybe you guys don't think that's so bad, but it just kills it, you know. All right. So I'm erasing Hall's theorem. Did you guys cover Hall's theorem in? Just wondering. Anybody that took 320 or 326? Did you do Hall's theorem for bipartite matchings? No. It's one of the most iconic theorems in discrete mathematics. I think it's maybe one of the number one. I can't think of another theorem that's as big as, you know, but probably it's the biggest. It has tons of applications. Okay, so let's get to the point. You guys have a test. Did you see that posted up?
Yes.
See that? Okay.
I need help with understanding 1 and 5.
Okay, let's go over it from top to bottom. So one of the problems it talks about ERP, right? Is that number 1 or?
Yeah, number 1.
Okay, yeah, let's take a look. Let's take a look at that. Okay, I realize you don't have much time. You have a 1 week turnaround, so I have no trouble with giving some hints and some explanation of this stuff. Okay, so what is the story with you have a code where let's say that you start with. Let's start with so it's n equals. We start with this. And we're going to do I equals 1 through 4. So when I is 1, we're going to swap the first component randomly with any of them, right? So there's 4 possibilities. You can swap with itself, with 2, with 3, or with 4. Okay, so that random function there means when I is 1. It could either be 1, 2, 3, or 4 with equal probability. Is that clear or not? We're not.
Okay, I don't understand what I is.
Oh. Let's take a look. Okay, I is the index on the array. So, for instance, if this were A, if this is A right here, okay?
Okay.
So A sub 2 would be 2. So so when A sub I, when I's been specified to be like 3 or something, that it's the third, whatever it happens to be the third component.
So I is the index.
Yes.
So right now they happen to match. And then what we're doing with I, can you say it one more time?
Okay, it's gonna, unless I wrote it wrong, which it's possible. I should go from 1 to 4.
It's okay. I goes from 1 to 4.
So when I is 1, with the first go through, we're going to swap A sub I with A random. So I is 1. So A sub 1 with A random, 1, 4. So that would be you're swapping randomly with whatever's in the first, second, third, or fourth component.
Okay. Yeah, it's more just I'm a little slow on this notation. So swap.
Let's do it.
Okay.
Let's do it. So suppose this is what you start with. This is 1, 2, 3, 4. Okay. So you start with 1, 2, 3, and 4. Now let's take I equals 1. What's going to happen here? Well, you're taking this and you're going to swap A sub 1, which currently has a 1. Uh-oh. Oh no, something. Oh no. I'm getting
okay.
There's a slight problem here. I'm sorry, you guys. Can you see me? Because it's got something going on. It decides unexpectedly to tell me I need to upgrade some software, and I hate it when it does that. So I think my only option is to move out. Oh, there. We're back to normal. Well, it knows when I'm trying to explain something difficult, doesn't it? When will the file be assigned? let's after I collect this one, okay? Because I don't like piling on stuff. So we take care of this test, and I get the key out there, hopefully graded. Then I'll hit you with the final. Final won't be crazy, right? Crazy problems were on the midterms. I'll make it reasonable. Okay, where were we now? So I equals 1. So you're swapping what's in the first component randomly with this one, this component, this, or this. So we can look at those 4 possibilities. If I swap with 1, then you get the same thing. If I swap with 2, I get this. So I'll stop when I do this. I swap with 3, 3, 2, 1, 4, or I swap with 4, what do I get? 4, 2, 3, 1. Okay, so each of these outcomes has the same probability of a quarter. Okay, I'll stop there. That's when I equals 1. So with a probability tree diagram, we're looking at each branch is a different outcome, and we're because it's randomly chosen who we're going to swap with. Those all have the same probability. I'll stop there. Is this okay? Or Abe, you're looking at it?
Okay. Okay. So yeah. So we're seeing that looking at I equals 1, you're swapping. It can swap with itself.
Mm-hmm, mm-hmm.
So we have 1, 2, 3. Okay. So far, so good.
Now tell me what happens at I equals 2.
So when I equals 2, we don't start over from the beginning. We go from here. Like we make 4 branches for each of the branches.
Or
excuse me, 3 branches.
Because you're going to swap. Okay, you're looking now at the second component. You should be looking at A sub 2.
Right.
You're going to swap this with either what's an A sub 2 itself, A sub 3, or A sub 4. So there should be three branches there. 3. Mm-hmm. Is that okay? So let's do it. This is the crux of the matter. So if I swap with itself, what do I get?
We still get 1, 2, 3, 4.
If I swap with 3.
1, 3, 2, 4.
Yes.
And 1, 4, 3, 2. I think. I hope.
1. Okay, so I'm swapping with 4, right?
Yeah.
So 1, 4, 3, 2. Very good. Right.
Okay.
These are all equally likely. Okay, because of that random function and that built-in random function. So this is not meant to be a hard. However, if you're going to prove this, the probability tree diagrams are sort of a K through 12 kind of technique. If you want to prove this, and how would you prove this in general? You'd have a huge diagram, right? So you need to have some way. That's what I was trying to hint at. That maybe you could look at CLRS and see what they're doing, and then just I'm giving it to you basically. I just want people to focus in on what would happen on the next one. So how many branches would you have here? Now you're looking at what? You're looking at the third component, right? So what would you have then? Help me out. What would I get on this one?
Yeah, we get 2 branches each. So 1, 2, 3, 4, and 1, 2, 4, 3.
Very good. Right. Okay. Right. So now what happens on the very last one? So this is I equals 3. So if you have I equals 4, what's going to happen now? Now the 4th component can only swap with itself. So you don't get any.
We're basically done. Yeah.
Yeah, you're basically done. These just go down. So the question, this problem was reasonable. What is the total number? What do you have to do to finish the problem? You've got to get all those leaves, and you have to verify that what?
Individual, okay. There's 4 factorial different orderings. You need to show that each ordering has an equal likelihood
exactly.
of happening.
How much is 4 factorial?
24.
So, I don't know how many leads there are. I mean, these are things you'll do when you work out the problem. But, if you have 24 leads, I guess...
4 times 3 times 2.
Well, you're doing it now. So.
Yeah, sorry.
Yeah, so you better have each permutation showing up once.
Right.
In this problem, okay? So, they're not meant to be... The thing that's hard about this is if somebody asks you to prove it, that this has a name. This permutation routine is called sort in place. Sort in place, and the question is, does it work for n? For n things, and then you have to be somewhat careful. We can't just count leaves and stuff. We have to approach it. Like, where's the induction step? Because it's. I just checked it before I went on line here, and I checked to CLRS, and they say it's going to use induction. I don't know that there's another way to do it. But if you can
wait. Well, now I'm curious. So, but we don't have to do that because we're not proving it for n, are we?
Exactly.
Okay.
Right. But you need to. Okay, we draw a picture here, right?
Right.
But still, there should be this. The other part of the problem was to do it. You did prove it sort of with the.
Right. Yeah. No, I see that. Part A, Part B. We should use it using probability theory.
Yeah, you should try to do that, because once you do that, then. And I wouldn't be surprised if you did it by induction.
Okay.
Wouldn't be surprised at all. That's how they do it in the book. So maybe you could find a better way because it's so small. It's only 4. But if you've seen CLRS, it's sort of mysterious, this type of thing when they do it in the book, because they're doing it for general n, and the proof looks formidable. It's like, there's a lot of stuff going on. What's the induction hypothesis? I mean, that they call the loop invariant in their book, but there's only the induction hypothesis. I don't know. I just like you guys to look at this stuff, because if you ever do any programming, there's definitely going to be some randomization, at some point, and it shouldn't be adverse to working with it. Okay, so that was one problem, right? You said there was another. So we're good. How about anybody else? Let me check the chat. In case you come in late here, I announced that the due date is due soon, right? I mean, we have basically a week or something to do this.
Yeah, it's due a week from today. Did you put a time? Because I know you like to have it turned in at a particular time.
Yeah, let me check.
I think he said 6 p.m.
Okay.
Yeah, but I got the wrong date. Damn it. What the? Oh no! I didn't fix the date. Crap.
Is the date not May 11th?
No, I was copying off another test. Hold on. That's. I don't know how this happened. I was copying off another test, and I think I'm going to have to change. Okay, I'm going to have to make a note to fix the date. The date should be. It should be May 11th.
That's what it is right now.
Huh? Say again.
Wait, what I'm looking at says May 11th.
Well, what I'm looking at is all messed up, so I don't know what's going on. Oh, I'm looking at a back test. Okay. Okay, now where's the real test? I don't know where it is. Okay, well, if it says May 11, that's the correct, this a week. But, now you know my secret. I use back exams and simply change the numbers. But, well, okay. Okay, so you also mentioned about number 5. Let's see if let me just find the darn test, though. I'm concerned about it. And I have misplaced the test. Hold on. This is not good. It's going to take a second to find it. All right. Okay, this is not good. Can you remind me what that problem was? Because what was the fifth one?
Sure, I can read it. I have it open. A bin
Okay.
of 6 transistors is known to contain 2 that are defective. The transistors are to be tested one at a time until the defective ones are identified. Denote
Yeah.
N1. Good so far?
Yeah, but I took this out of a source, so I haven't really looked at what was your issue with it though, so I know to.
I don't get it. I'm sorry. I don't understand the situation. So let you read the whole problem. So yeah, you've got a bin of 6 transitions,
Yeah.
and so 2 are defective. They're going to be tested one at a time until the defective ones are identified. Denote N1 by the number of tests made until the first defective is identified, and N2 is the number of additional tests until the second defective is found. Find the joint probability mass function N1 and N2. Are there so like we're pulling things out one at a time, and then we're not. Are we putting them back again?
No.
Okay.
No. So this is like a hypergeometric sort of situation.
Yeah, it's hypergeometric. Okay.
Yeah, and you're. But this is sort of an interesting thing. So this is measuring how many more additional pulls to find the other one. So you've definitely at one point you get the first one, right?
Yeah.
But then after that, how many? So this is a small number. 6 is kind of small. It's sort of a baby thing, but this is a neat idea, though.
It's fine. I'm happy. It's a small number. That's great. Sounds great to me.
Now the 16. No, I'm kidding.
And it's been over a year since I did 341, but I'm trying to remember what we mean by joint probability mass function.
Okay, let's do an example from the book on that. Okay, because
Sure.
we're dealing with a discrete situation.
Yeah, I noticed that it is discrete.
So basically, you have 2 random variables, right? So let's do an example. Let's get double duty out of this. Let's give an example. If I can find the NOR zones. Okay, so let's do a simple possible example. Example 1A. That's supposed to be E. Okay, so a situation here is I have an urn with 3 red, 4 white, and 5 blue. And you're going to select 3 at random. Okay, now comes the more than one random variable, okay? You're going to have 2 random variables. So of that random sample, and this is without replacement, we're pulling them out of there. From that random sample, X will be the number of red, and Y is the number of whites. Now, so what we want is the joint probability mass distribution density. So, probability mass function in the case of a discrete random variable. So what does that mean? Well, we need to calculate certain things. Let's do one of them. So so you're looking at probability mass function always has a lowercase. So it's got 2 things here. Okay, so X would be the value of random variable X, and Y is the value of random variable Y. So this has a probability associated with it, okay? It's 2 random variables, but what's the chance of the first one being X and the second one being Y, okay? So, for instance, you could look at probability of the first one is 0, so no reds and no whites. Okay, so we need to fill in this information in a table or something. So let's see if I can avoid the washout so I can get my full table in here. So the top would be the number of white, and the bottom one on the side here is the number of red. Okay. Okay, so the way they do these things is they split it. They split this. So this is the white, and the red, and the eyes are the reds, So these are the different situations. These are the different possible outcomes. So let me ask you a question. So if you want to figure out what goes here, so this is the joint probability mass function for this problem. Okay, the two random variables involved are the x and the y, number of reds and number of whites. So what would be the probability of getting two reds, two reds and two white? Let me just make sure I've got the eyes. This is one more line here. Probability x equals y. So this is this line here. So this is different than what normally happens. So this is the line for x's. Excuse me. No, this is okay. This is the reds are. This is the line for x's. Okay, and so this would be the marginal distribution of just the probability of just looking at random variable x of getting a certain number of reds. But I'm asking about this question right here. So what is the probability of 2, 2 if we're going to calculate this?
0?
It's 0 because you can't. You have a sample the size.
Right, you have a sample
3.
size 3,
So this
you can't have 2 and 2.
Right. So this simplifies. So which are the ones that we can crawl out of here? So it can't have this. It can't have this. This. What else? What about this one? You can't have 4. But everything else we should work on. So what about 0, 0? What's the probability that I get 0 reds and 0 whites?
That's
Okay.
the same as getting 3 blues.
How many ways? So how many? Right. So how many ways? This is all we have to calculate this.
5 out of 9 to 12. No. Oh God, I'm bad at this. Hold on.
Well, we haven't done it. We haven't done it for a while. So you're gonna. This would be the number of ways to get. So we're not getting any reds and whites. So it's all blues. So it's there's 5 blues to choose from.
Okay, so yeah, I should just use hypergeometric instead of deriving it.
No, it's not necessary. No, nothing. No, this is a flat out sample. I mean, we did this before, like with car.
Oh, okay.
You don't need anything fancy. So how many ways could I get all of them being blue? Well, we just figure out, well, how many ways could you make that sample? I mean, how many ways could we grab 3 from this? So how many are there altogether?
There's 12 total.
Good. So this is like, remember, like hands of cards or something like that. So how many? So there's 12 total. So there's 12 choose 3 ways of selecting 3 of them there. Now, how many ways then do we select them so that there are no reds and no whites? How many ways can be done?
5, 2, 3. Yeah.
Are we good with that? Now, what is the number? So 12 choose 3 is what? Is it 220 or something?
Later.
Yeah, I think it's 220. It's good. But this, I don't know, I should know that. Is it 15?
5 choose 3
10?
is 10.
10. Okay, so that means that in this location, it's 10 over 220. Hey, my only problem is I'm not used to this format. I've got to keep track of which ones are the reds and which are. So I's usually are rows. So this must be the number of reds. Let's try one. So what about this? What about this thing here? So in this case, we have what?
2 reds and 0 whites.
3.
So it's really 2 reds and 1 blue.
Okay, let's do it. You might say I'm wasting time going through this table, but there's an ulterior motive here, because I want to explain to you what it means for the 2 random variables to be independent. We know this is not independent, right? Because if you take gobs of reds, you're not going to have any. You're not going to be having any whites, right? So, but we have to define it here. So which one were we gonna look at? This one or so? It's the same denominator, but now we get one red. So 3 choose 1, and no whites. So times 5 choose 1, right? So that should be 15. Oh crap! I get 2. I want 2. I want 1 red and 0 white. So from the blue, I take 2.
Two blue.
That's 10, right? So it's 30. Should be 30. Okay. So how about taking something? How about let's do this one right here. So in that case, how many reds are we saying that we have? So in this case, you have 2 reds. So 3 choose 2, and then 1 white. 4 choose 1. So that should be 24 over. 3 choose. That's 3 times 4. Which one was I doing? Oh, this one down here. Okay, so that's 4 times 3 is 12 over 220. Okay, let's pick on that one right there. So actually, I just, just to save time, let me put in the rest of the numbers here. 40 over 220, 30 over 220, and 4 over 220. Okay, so what goes in this marginal column here? So if what you've done is you've broken up the case of no reds into disjoint sets where no reds and no whites, no reds and 1 white, and so forth. You've broken it up. So the probability of getting no reds, period, it would be the sum of these probabilities. It's called the marginal distribution. So what would that be in this case? 50, 80, this looks like 84. So you're back down now to a 1 variable situation, okay? If you're just looking at the number of reds. And 108, there's that number again. And what's this 27 over? And what do we know about these numbers? What should happen? If you add up all these numbers, what should you get here? Well, one of these outcomes has to happen. Either you have no reds, 1, 2, 3. That should be 1. Okay. Now, where does the probability
So what I guess the main thing is I'm just trying to remember what it looks like. Would it look what a probability mass function looks like? Would it be 3?
It just has it has stuff like it has this 1, 2, 3, 4. I mean, in general, it's a discrete thing. So you have for the outcome, whatever the outcomes are, you have a probability associated with it. Right?
Excuse me, a joint probability mass function.
Oh, well, there's no.
That 2-dimensional.
It's actually
Okay.
sort of a three-dimensional picture. You have different probabilities these are like different cases that it could take on, right? Different values, and when you add up these probabilities of all these values, you also have to get 1, because how do we get this here? They're adding up by row, right? So you're basically adding up all of these. I didn't give you all of them, but they should add up to 1. I can't see it.
So, but if we're going to just write the probability of x comma y for whatever given x and whatever, or the probability that x equals I, and then the probability that y equals j,
yes,
is 3 choose I, 4 choose j, 5 choose 3 minus I minus j, all over 220.
Well, okay, but aim. Let's just try something a little less ambitious. I mean, I don't know.
Okay.
You want. Okay, this is the joint one, right? So let's take. Let me just put these in so we have the whole story. I don't know which one I want to pick here. I could get unlucky and pick one that does. See, in order to be independent, for these variables to be independent, that means you always have to have the case. You always have to the case that this is splits like this. I think you were about to go there, but this is this. We can take this as.
No, I wasn't. I'm really just trying to understand how to what the answer to number 5 is going to look like.
Oh, I haven't. I haven't looked at it.
Like I don't. It's not a number. What is it going to look like?
It's going to be. It'll be something like this. That you want the joint probability.
Okay, you want us to make a table?
Yeah. Yes.
Okay.
Yes. Oh,
great.
yes.
Okay. So that.
Yeah. No, I'm sorry. Sorry about that. No, I didn't know what you were. I thought you were hinting towards independence or something.
I totally get that there's things that we can show about this, but I don't know what I'm supposed to do.
Oh, right. Give the exactly. Okay. So what you want is all these. You can list. You don't have to put them in a table. I could just list them out. But there's a finite number of outcomes. With I equals something, J equals something, and equals what the probability of hitting that outcome. Somebody says can't see. I'm sorry. Where was I? Can you see it now? Or I keep on infringing on the view. So this is 1 over 220. Why is that so small? This is 15 over 220 because there's only one way. If that one's small, there's only one way you can get 3 reds. You take all the red ones and nothing else. That's why it's that small. Okay, so what I want to do now is show if they're independent, this has to happen for all I and j. We have to split like this for all I and j. Can you find one where this has not happened? I feel like I have jet lag, so I have to take a little peeks here. Which one should we pick on? So, which one should we pick on?
I don't know. Just try one.
I could get very unlucky right now. But it has to happen for all of them. So let's pick. I don't know. I'm looking at this right here, and
sure, we can test it.
So I is what? So what are we dealing with? I is 1, right? I is 1, and j is 2. And we know what this number is. I copied it out of the book. Well, why is it 18? Well, that's the calculation. Okay. I feel like a crappy teacher. How do I get 18 out of this? Well, I've got 1 red, so there's 3 choose one way to get that 1 red. And now I want 2 whites. 4 choose 2. So that's 6. 6 times 3 is 18. So 18 is in the numerator. That's how you get that. So anyhow, what is the result of that? So it's 18 over 220. Now I've got to be careful. So what is the probability that I get 1 white? Well, that turns out, okay, so we have to have this marginal distribution to get that. So we have the probability of getting 1 white, and there's these different, 1 red is summarized by this marginal thing here. So this is x equals, in our case, we're going to look at x equals 1. So we know what that is. It's 108 over 220. Now the thing I don't have here is what's the probability of getting, this is a 1 and this is a 2. What's the probability of getting 2?
We could sum going down 30 plus 18. So 48 over 220.
48, exactly right. So I need this. Did I just hold on a second. The red one is the 108. So red, yeah, right. So down. So we're talking about 2, right? So we have to go down. So that's 48 over 220. Now, if these are not equal, if that's not equal to 18 over 220, then they're not independent. This is the case, we've just shown. But I don't know. We use the calculator. Okay, so 108 times 48. I'm getting 324 over 3025. How could that be? $3,025.
Okay, I'm getting 5184 over 220, or 220 squared. I just didn't simplify it.
Wait, 324. I know. Is that possible?
Okay, well, that's simplifying stuff. But yeah, we can just say, okay, well, that's not equal to 18 over 220.
Because if it were, it would simplify down to that. Well, that's not in simplified notation. But that's just I don't want to leave the stone unturned. So if they simplify that one, it's 9 over 110, and this calculator is going to simplify. So these are not equal. So it's not independent.
I feel like you could probably get a better feel of it by looking at 2-2. Just
2-2.
because, yeah.
Okay, because you're getting.
Because you're going to get a number that's not 0, and then that's not equal to 0. But
Yeah.
But
Well, they're
regardless,
also,
it doesn't work.
Right. We know that because, if you're taking more reds, then it's going to be less. It's going to influence the distribution of the whites you will take after that. More reds mean less. Actually, oh my gosh, I'm going to think about this. If you take in more reds, that should increase the chance. Let's see. Oh, whatever. I have to be careful here what I'm saying. But definitely it's influenced by the number of reds. Yeah, if you take them all reds, you get no whites. I mean, what's more simple than that, Okay, the other. I think that's. Yeah, we didn't do the marginal distribution here. But the other problem that I wanted to help you with was this. Not the transistors.
Number
the
2?
Yeah.
Because I actually spent this morning looking at number 2, and it took me a while, but I feel like I got it, and I'm hesitant to say anything because I don't want to give anything away.
I will do a similar. I'll do the problem in the book, not the problem I gave you. I'll try to do the one in the book because this is similar to a problem in the book. Yeah, this morning. What did I do this morning? I was listening to the Telemann viola concerto.
Oh, the Telemann viola concerto.
It's pretty good.
I mean that was kind of like my first big concert actually, where I was a soloist. Was
Yeah. It's good. It's good stuff. It's good stuff. Okay, so let me look at number 2. Let's see. I'll try to find notes. If I don't have notes, it's going to be embarrassing. It's already embarrassing.
What performance is this? I haven't heard of it.
Oh, it was just I guess it's a fairly classic concerto, right? I mean,
it's one of those things that you just have to learn as a violist.
Yeah.
And like it's just right in terms of difficulty for someone who's just kind of entering solo concerto work.
You're talking about a piece.
Yeah, no, that has nothing to do with this.
Cool.
You could turn that around and say, are there any inappropriate concertos? There's all this crazy stuff out there, right? I mean, there's crazy, like Liszt has some variations, whatever, that are just unbelievably technical. Which ones were that? What was? There's the Devils. What's the violin concerto? The Devils. I don't know.
I don't know.
You know the one I'm talking about.
No, I don't.
Oh.
If you're talking about that, it's probably something by Paganini.
Yes, right.
Yeah.
Okay, so let's.
I don't know why. I don't remember playing any Paganini, but for some reason in my ancient history of when I played my violin a lot, that name is now synonymous with pain somehow. I just brought up.
Yeah, well, because he literally had a degenerative muscle disorder that made him a god at playing violin. So
wow,
that's why it's always called the Devil's whatever, because he was assumed to be possessed.
Well, there actually is a devil. There is a Devil's. I forgot. My son found it, and and I showed it to I have a colleague who was trained to be a professional violinist, and he got out of it at some point, but he was very
Good for him.
amused how difficult. He was just amused by how difficult this piece was. If you look up the Devil's Violin something, you will go right to that, I'm sure. Okay, so let's look at this example. So what I'm trying to do here is get you guys a jump start on the problem. I call it the arrival time problem or the waiting problem. So let's we're looking at 2C in the book. Not to get the precise. Okay, so a man and a woman are going to meet between 12 and 1 p.m. So a man and a woman are going to meet at a certain place between noon and 1 p.m. So arrival times, they don't say like this in the book, but really the arrival times, time for each are uniform. So the first step we have to do is decide how we want to handle the units here. So what do I mean by times are uniform? Well, if this is 12, this is 1, each one independently, okay, this is important, independently, each one could be anywhere in that interval, okay? So they can't be outside of that, but so how do we look at this from a probabilistic standpoint? That's a uniform, each one has a uniform distribution from 12 to 1, right? So we know now what the distribution is. It's not normally, normal distribution would be if this happens over and over and over again, and you can start saying, okay, if you start taking averages, then you get into a normal distribution. But this is a one-shot deal. And the question is, what is the probability that the first person of the couple to get there, or somebody said to me, for what is uniform? Oh, okay, so let me this is the uniformity. Okay, 12, here's 12, right? That's the earliest time, and here's the latest time. Then the density function of the arrival time for, say, the man looks like this. This is called a uniform distribution. So between here and here, it is 1, and off of this unit interval, it's 0. So it looks like this. That's a uniform from 12 to 1.
Okay, so the man is arriving sometime between 12 and 1, and it's random, it's uniform. And the woman is also arriving sometime between 12 and 1.
Right.
Okay.
Right, but I got a chat here which said, "What is uniform?" The way to answer the way to answer that is that the density function looks like this. So in other words, it's no interval is more like interval the same size is equally likely to be in intervals of the same size. I mean, I don't know how to say this, because to say, well, every arrival time is equally likely, yeah, they're all 0. Okay, that doesn't help, because we're talking, when we have continuous random variables, we talk about intervals, essentially. In our book, it's intervals.
You could just arbitrarily divide it up into minutes and then say, well, every minute is equally likely.
It sounds like there's a little bit of physics in you still, because it sounds like you're discretizing the problem, which is nothing wrong with that, okay? It's happening. It's making a discrete problem out of a continuous. This is how things get done on the computer eventually at a certain level. Okay,
yeah,
let's talk about the units, you guys, because isn't this awkward to talk about clock time? Because it's like a funny thing. To get started on the problem, we have to change the units to something that's more manageable. So what do we do? I don't want 12 to 1. What do I want? It's funny. It's like the hardest part of the problem is the stupid.
Make it 0 to 1?
Yeah. Well,
Okay.
Okay, but it's this the choice of units makes a huge difference in how this plays out. It's crazy, you know. It's like Ross doesn't say that. He's so, you know. But I think we should be talking about x. These are the two, right? 0 to 60. That way we can. It's just we can see this better. And y is uniform also from 0 to 60. So the question that's asked here is, what is the probability that the first person on scene has to wait more than 10 minutes for the other person to show up? 10 minutes or more. It doesn't matter more than or 10 minutes more. We've got a continuous distribution. This is an interesting, starting to get an interesting problem, right? I mean, we started thinking about this. Do you see that?
Did they wait 10 minutes or more?
10 minutes or more.
Okay.
Okay. This definitely is a joint probably situation here. Okay. So how do we picture this? Well, first, what is the condition? So let's put down. I don't know where to put this without getting a washout. We want the probability that first person to arrive waits more than 10 minutes. And the one on the test is similar, okay? So this is, the one on the test is similar. So what is the condition on these two random variables that you get there? So how do we write this mathematically? How do we write this? Let me finish off the coffee here. How would you write that? So how about what's a concise way of writing that? The arrival time of x and the arrival time of y. What is the relationship that you have to wait? Say one of them is going to wait more than.
Would you subtract the two?
Exactly. Right.
X minus y?
Very good. And this is greater than or equal to 10. That would be the condition, right? The probability of x, and it's sort of, it's a symmetrical kind of thing. So the question now becomes, well, don't like absolute value, but how can we break that absolute value into two different? Now let's just do a scratch here. What if somebody said, well, the probability that the absolute value of z was some random variable, is greater than 10? How would we picture that? Well, it's 0. So it could be, you have the case where z would be bigger than 10. And also, we would have the case where z would be less than 10. So let me draw that bold. So really when you have an absolute value which is greater than there, you're dealing with two cases. And we have to, whatever we do in the answer here, we have to, well, we look at the symmetry. Whatever one of these, we do one of these cases, we'll multiply by 2, okay? This is how we handle the absolute value. So, okay, so tell me what we need to do here. So this would be what? The probability that what? That x without the minus 1, this is greater than 10, plus what's the other case?
Probability that y minus x is greater than 10.
Yeah. So, but this is a symmetrical situation. So we just go 2 times one of these.
Yay, symmetry.
Right. So, but okay. So let's let me just make sure this is not how I do these things. I put a minus sign in front of this. This is okay. I'm sorry. It's a creature of habit. So when I look at the other case, I go minus x plus y greater than 10. So it's the same thing, y minus x, but I always think of it that I put a minus sign in front of the absolute value. On the final, there might be a random variable squared, right? And you might have to take the square root of it. I just want to make sure you don't blow this on the final. When you take the square root of something squared, What is that? It's important when you.
Yeah, it's always positive.
Take the absolute value.
Or like, yeah.
We have to do that. Otherwise, everything goes to pot. Okay, everything goes to pot. So just be aware of that. I mean, that might creep into the final as a problem.
Yeah.
Copied out of the book or something. Okay, so let's take one of these cases. So we know that X. This is okay. So this is again. I'm in this problem with a washout here. I wish I had more space. A refrain of everybody that lives in San Monica in an old apartment. Okay, so this is the origin. So X is this way and Y is this way. So I think that A was asking me about this. You know, how do I represent the joint distribution here? Well, look, this is a uniform. Any combination of X and Y or regions is the same probability. It's just a question of area. So this rises to what? It's zero. The joint distribution, the density of this is zero outside of this footprint. But on this footprint, how high is it? How high is this plateau? We're looking at this.
The whole thing is going to be 1.
Right. So
Yeah.
So in order to make that 1, we're showing the density, which is kind of what you were asking me earlier, but in a discrete case. So picture this. This thing pops out to what height to make this whole thing 1?
1 over 60 squared.
Yeah. So 1 over 3,600, yeah. Okay, so our job is to figure out one of these. So say, did I erase this one, say. So if I'm looking at X minus Y is greater than 10, I have to play
What's
with
1
it.
over 3,600?
Exactly, right, 60 squared, right.
No, what are you saying is that?
This is a density for the joint distribution of X and Y. Okay, so this to make this a probability distribution, the volume here has to be 1. So what height does this have to come to for it to add up to 1? Well, it's the base is 60 squared, so the top has to be 1 over 60 squared, right? To get 1 here. Right. This is the analog, the 2-dimensional analog of just the uniform distribution in one variable, which is a pop-up. So it's like a box function, but this is like what does that point represent? Well, or say
I don't know what that represents. I don't know what we're looking at.
Person, let's say X, the man, he got there at 15 minutes, and the woman got there in 20 minutes.
So that's a point.
Yeah, so it's this point. But because we're talking about continuous random variables, we're talking about regions, But that point, this point will result if the man gets there in 50 and she gets there in 20. So these are all the possibilities that can happen in like every same area here. It has the same probability. Okay, so we want to know which area corresponds to one of them having to wait 10 minutes or more. That's what we really wanted to see. How are we going to do this?
Oh.
I mean, if they both get there at the same time, that doesn't count. Like, take this point right here. Nobody had to wait here. They both were as late as they could be, right? Both were 60 minutes. So there's no, never let somebody wait. No, I'm kidding. I shouldn't be giving advice. Okay, so let me see if I remember how to do basic algebra. So greater than 10 minus x. So that's equivalent to what? Well, it's equivalent to writing crappy. I need to write clearly, okay? Okay, so what is it? So x, so minus y is greater than 1.
10 plus x. Or 10,
10 minus
x.
Y is what?
Less than, yeah, x minus 10.
Right. Oh, this is some sort. Okay, well, where exactly is y equals x minus 10 anyhow? I mean, this is why you take pre-calculus so you can draw a line. So I'm sorry. Sorry, I'll get fired for these comments. But anyhow,
Well, it's got an x-intercept of 10. So I started at 0, 10, and then a slope of 1.
okay. I'm sorry. I'm getting. I think I've had it this semester, but we have to. It'd be nice to put some grid marks down, right? Now I taught pre-calculus, and sometimes it was not a comfortable experience because even with this situation, you're supposed to put grid marks, right? I kid you not. For you guys who'll be teachers, I saw stuff like this. The grid marks were not uniformly distributed.
Turn.
That's way far off.
Something you have to deal with as a teacher, because what does that mean? That means they don't understand the contribution of the Cartesian, somebody Descartes, because he had this idea, where you have uniform grids, that if you don't have uniform grids, you're talking about, like something with logs are getting involved or something, whatever.
Mm-hmm.
But let's make nice marks here so we can make a decent picture of this. Okay, that's 60, so that means 30 is in the middle. 20, 10, 40, 50. I guess I'm suffering from the same fault that I'm complaining about. Okay, so let's find it now. As Ames said, it intercepts at -10, so that means it goes from where to where?
Well, I went to the x-intercept, so 10 and then 50 on the other side.
Very good. And that's supposed to be a straight line.
Right, and we want the area that's below that.
On y is less, right? So, and there will be another thing here, but but we're going to just multiply by 2 in this case.
Right, yeah.
So I don't need the book. Is addicted to using, to integrate simple things to find the area of a triangle. But I remember the area of a triangle is 1/2 base times height. So we could actually answer the question now, I think. We have enough information. So this answer is 2.
That's an interesting graph.
Times red. Thank you. 2 times red. And that's equal to 2 times 12. Well, how much is the red? So it's 1/2 base. And what is the base? The base is this, right? How much is the base?
50.
I was worried that maybe I just got cut off there. 50.
Oh, you were saying that each grid square is going to be 3600. Now I get it.
This is not discrete. This is okay. Be careful, Ethan. We're in the continuous.
I know, but that's what you were saying earlier.
Not
So that's why I got confused. That's why I was confused, because I was like, this isn't discrete.
Oh,
now I see.
Yeah.
You're just doing a unit conversion of like.
Oh, are you talking about from like 12 to 1 as opposed to 0 to 60 or no?
Yeah, this whole space represents 60 times 60 minutes,
yes, right.
which is 3,600 minutes. So
But that's
then we just divide by 3,600 to get to get the unit to get 1.
Yeah, right. To make it 1, right?
Okay.
So we could figure out, like for instance, what's the probability of lining the red? It's red over the whole area. Because then that scale factor you're talking about would cancel out. Okay, so let's see if we even get the right answer. There are answers in the book. So what's the height of this? I've made a mistake already because this is a probability, I need to divide by what?
60 times 60?
Well, no, I mean the whole, I want to know the proportion is this, so I have to divide by the whole area here.
Right.
So, but that's 60 squared.
Yes.
So 60 squared. So what is the final? Nobody can probably read this, but it's 2,500 over 3,600.
Yeah.
And I don't know, so 25 over 36. So if you were doing this with an integral, you have to multiply by the joint probability density function, okay, which is 1 over 60 squared. Or maybe I should do that. But anyhow, this is the whatever the non-calculus way of doing this.
That's really interesting. I bet if yeah, that's kind of funny because it's like 10. If I don't know what I'm trying to say. It's just 50 over 60, and that like 50 minutes is like that's 60 minus 10. So I bet like if it were 20, it was like probability of them more than 20 minutes apart, then it would have been 1600 over 3600. There's like a pattern.
Well, don't forget the 2, but anyhow, so yeah, right. With the half multiplies by the 2. Okay.
Yeah.
What is this as a percentage? I mean, now you got me interested. Now I'm trying to wonder if I could have guessed the answer. What is 25 over 36 as a decimal?
I don't know, but it's 5 squared over 6 squared. So that's like
It's around 70%.
I feel like if it were 20 minutes, then it would be 4 squared over 6 squared.
Well, you know what? Unless I
30 minutes would be like 3 squared over 6 squared.
I mean, just think about the setup of the problem. That means that this delay. I mean, this gap between their arrival times is to get a gap like this is quite common. Somebody's going to wait over 10 minutes. I mean, that's just the way it is.
Interesting.
It's this. I remember the student joking about this the last semester when we talked about it. He said, "Well, this relationship won't last long." Because nobody wants to wait. 10 minutes feels like 20 minutes, if it's a first date or something, right? So let's see, if you're going to do this with calculus, what do you have to do?
Integrate area under the curve.
Well, let me
I don't know.
let's be careful here. I mean, I don't want to. What is the formalism that's expected? What's the formalism? I don't even know if I wrote it down because I like to do things simply. Let's see if I wrote it down here. Yeah, so of course now I've erased what the condition was. So y is, let's check this one. I don't think this is, so y is, so what is this one here? It's the opposite. So let's just do it. Let's do the formalism for y equals x plus 10. So we'd be doing it for this other, looking at this here. Let me get rid of this. Okay, so what do we have to do? Double interval. Now here's that joint density function. And what is the region of the support of this thing, density that we're looking at here? So y is greater than x plus 10. Okay? That's a double integral. Well, the way it works out in the book is that you can always, if they have certain shapes, like rectangles are easy, they can be split. Triangles are good, but remember, just think though, if it had even a circle might be more complicated to describe. To split into iterated integrals, you have to be careful, or some weird shape. So now these steps are all important. So it's still double integral, same region. However, because these are independent, these two, the people show up independently, and their times are independent of each other. That means that we can split the joint probability density into the the individual densities of x and y. Okay, so that's a crucial step. And so what are these densities? Well, x goes from 0 to 60, right? So 0 to 60. So you have to divide by 60. It's a simple density. 1 over 60 is 1 over 60. So it's 1 over 60 squared. That does these. And now what? Well, to integrate this region, so y goes from what to what? Let's do the y. So y goes from 10 to 60.
I'm a bit confused. So our limits are we're going in terms of 0 to 60 for the limits.
Yeah, but we're integrating this region right here. Okay.
Okay, no, I don't.
So y goes from 10 to 60. See, we're going to do the y on the outside. So then
Okay.
So the y right for this region, the y goes from 10 to 60. But then where does the x go? I'll ask you this, Ethan. So where does the x go? If you know y, then the x is what?
Wait.
Well, okay. So what? Okay. So look,
What was it again?
this is. Let's look at that line right there. What is that? Y equals x plus 10, right?
Mm-hmm.
So definitely your x goes from
Oh, the x is y minus 10. Yeah.
to where it hits. It hits the. It goes from 0 to where it hits that line.
Yeah.
But that would be y minus 10, right?
Yeah.
And these have already been taken care of. They were simple. So what's the result of this? Well, it's 1 over 3,600. And let's integrate the inside thing first. So it's just 1 from 0 to 10. So that would be 0 to y minus 10. So that's y minus 10. So it's 1 over 3,600 times, well, what's this? It's a little messy. I like doing it geometry-wise, but I got to play, got to fight for everything. So this is what? Y squared over 2 minus 10y. I'm just trying to integrate this. Y squared over 2 minus 10y from 10 to 60. Maybe my body's in the way there. You can't see it.
I'm sorry. I'm still just. I've been a very bad student. I've been absent a few times. So.
No question. No question is too small. Maybe I made a mistake.
No, I want to understand a little bit more about how we do these double integrals. That 1 over 60 squared, like what is that?
60 squared. Okay, so these guys, the density function. Let me just do this as a sidebar. This was
Density function is 1.
This is 1 over
Right.
60 for x between what and what? Let's say equal to 60, right? But it's 0 else.
Oh, okay.
So it is as long as we're in that range.
So you're just scaling it basically. So like if we were to use like a standard thing, it would be like from 0 to 1, and the density function would be 1. So we're like kind of scaling
Exactly. You have to scale it because it has to be a probability density.
Okay. I felt like that's why it was there, but I just wanted to make sure.
Yeah, no, that's important. Well, this formality, we already got the answer, right? It wasn't fair. But this formality, what we're doing right now, is important because when you start getting into other regions or things that are the density function is not 1, or a constant noise as you go around, you have to be then you have to be careful.
But it's like you've said before, like getting in reps. It's good to be exposed to this stuff. It's a little bit
I'm one of those teachers that
easier.
that says
More
it
times.
doesn't do so. There's an old saying about that. Those who know do not speak. Those who speak do not know. It's like the death of teachers, Ames falling asleep now. So, she said, I've heard that before. Don't bother me. Okay, let's see if I got it right. I hope so. What are we supposed to get anyhow? So this is 60 squared. So 3,600 over 2 minus, what, 600? 600. And then minus what? at 10, so minus 50 plus 100. Okay, I don't know. Let's see how good my algebra skills are. Whatever. What is this? This is 1800 minus what? Okay, so it's minus 550. I don't know if that's right. What was the answer we got before?
The answer from before was 2,500 over 3,600.
Divided by 2.
I need to multiply this guy by 2, right? Because I've only done one side. So what is that? What is that number?
I think it's right.
It's 1250.
1250. Yeah, that's right. So when you multiply by 2, that's the right answer.
Because this is we need it. This is also okay. But so it looks a little bit different, but it's the same thing. I think I put a few people to sleep. Who needs sleeping pills? But okay, that's so. Look, I'm trying to help you guys out because the semester is almost over. So the problem I put on the test is it's very similar. To just change the numbers a little bit.
Yeah.
So, but it may lose a little bit of symmetry here. Okay, you know what I mean. You can imagine this. Maybe it could be different. It could come out a little bit different. So just be careful. The joke is that when I change the numbers, people go to Chegg, or at least last semester they went to Chegg, and the Chegg tutor blew the limits of integration. But holy cow, they got the right number. The answer was right. So I had to go back and say, look, this what you wrote in terms of the integral does not work. I had to calculate it wasn't right, but they put the right answer. Can you believe that?
So I know I should already know this, but when you're doing the integration method, what do you set as your limits? I think I can kind of see what it is, but and then your functions.
The key is you can write this as because of the region, because of the shape of the region, you can write it as an iterated interval. I'm trying to show you what the real truth of this matter is that most things that you might conjure up can't be, the double integral can't be, the region is complicated. It's not a rectangle, so that you can't get away with this, what they're doing. Okay, for instance, if you had to integrate over, say, some weird shape thing, like, not even convex, something like this. You're not gonna be able to do it. Okay, I mean, you can break it into pieces, maybe and stuff, but you're not gonna be able to do it. So everything has been set up in the book. It's artificial. It's been set up to be amenable to, if not one rectangle, a few rectangles, or parallelograms, or something that the area of.
Yeah.
All right.
But specifically then, so what is f of x, y again?
That's the joint probability distribution of x and y.
That's the probability distribution function?
Density. They mean probability density function, but in the book, continuously after they find out, they say the distribution. When you talk about the distribution of a continuous random variable, all of the questions about that can be answered by appealing to its density function. Once you know the density function, you know everything. You know the CDF. CDF. So when they say what's the distribution, they talk about what's this function right here.
Okay, so that's just the density function, and then your limits are the range of like events that you're interested in, basically.
Yeah, but right. I mean, this is the region, whatever region that is, because remember the region change. This changes depending on the region, right? Because it reverts to 0 when you go off that big rectangle.
Right. Well, I guess we're not also, so to be more specific, we would have to say that x is between 0 and 60, and so is y, right?
Right. Well, that's a very easy domain there. That's easy to do it. It's not complicated. It can get a little more complicated depending on the numbers I put on the test. It could be a little more complicated. Not much, but it could get a little different. Have I run out of time?
Right.
Or do I have time? What's the story, you guys? What do I need to do next?
We're already over time.
Yeah, looks like we're over.
I apologize for this. I hope I'm not wasting. I feel like I might be
No,
wasting.
that really helped. Thank you. It feels a lot more easy to me now.
Okay. Wake up that person over there. No, I can't.
Yeah, like it makes sense. I feel like I can really remember that.
Good. Well, what we need to do is read some of the examples where they compute marginal density functions and stuff for not in the discrete case, okay, in the continuous case. So I would read the simpler examples in chapter 6. Okay, so you just have to have, and I'm telling you, you might say this is all esoteric or useless stuff, but I have downloaded copies of the actuarial exam, and guess what? Yes, it's a standardized exam. Yes, they have multiple choice problems, but they're doing this asking you to do these kind of calculations. They want to know, does this person know how to integrate by parts? That kind of nonsense. But that's that first exam. It is this type of calculation. It's crazy. You're not really, you're learning how to compute and apply formulas. You're not really learning how to do problems from scratch that are non-standard. It's not required for that exam. But this type of thing is actually on the exam. It's multiple choice. So if you make a typical mistake, you'll get it wrong. So there is a value in going over these computational examples that he gets if you're going that route, towards statistician or data science. So yeah, I'm sorry I covered so little today, but I guess I got addressed a couple of problems on the test, and the rest of the test is. You said it looked decent, or?
Yeah, I think I can answer every other problem.
Good. Don't tell your group because they end up answering.
Oh, okay. To be fair, we've already got a document going, and there's already stuff there that's not written by me. So, don't worry, we're working on it.
That's called the delegation of work, right? Again, I apologize for not covering very much. I did that hike, and I'm not particularly focused, but I made it to the clouds, the cactus, the clouds. I did it, so. I don't know. I think that's something. Okay, I don't know what on the level of the personal accomplishments, but it's something. All right, you guys. Okay, I guess I'm out. I would like to keep going, but I would just be rambling. So okay, so for Thursday, read ahead. Read over some of these simpler computational examples, and that will help understand the what should I say? The machinery that's being used here. All right. Okay.
Mm-hmm.
All right. Thank you, Elizabeth. You have a nice day too.
All right. Thanks. I'm gonna get going.
Yeah, I'll hang here for a couple minutes if anybody wants to chat about the test or anything else, or tell them on viola.
Cool.
I played the bassoon sonatine. Have you heard of that?
No, I'm not very familiar with the Winds world. Oh, can you move for just a minute so people can copy the board?
World.
I'm a strings person.
Mm-hmm. Same here.
I can't remember the name of the composer, but he did a lot of scores for movies and stuff. So it's got a real grab.
John Williams.
It wasn't. No. This was a guy. He lived a long time, but he's French. Because it's what was his name? The bassoon sonatine. Wow, what a piece! It's the French have a way with flashy stuff. Somehow you can tell like French organ music. You can sort of tell it's got a lot of flair to it from the Romantic era.
I guess I'll see you on Thursday. I got a class to go to.
All right. Good luck with your other class. Good luck.
Right. Later.
Nice seeing you, Ethan.